Hey folks, welcome back. This is a redo of Lecture 25 because the originally posted Lecture 25 did not actually have audio. So this is a repetition of that, which I'm basing on the posted lecture notes. So this should be fairly representative of what we talked about in class. Last time, we were dealing with using the steady state approximation to deal with a fairly complicated reaction mechanism and to describe the dependence of that reaction rate on the concentration of starting material A and B, and actually even on the formation of product 1. This new rate law containing all of these terms led us to some interesting conclusions that if we were to plot initial rate during a reaction as a function of concentration of B, there would be some region in which the reaction was linearly dependent on B concentration, a second region where it would be less than linearly dependent, and then a third region in which the rate of the reaction would be independent of B concentration. The independent area is if the concentration of B is really large, or alternatively if K2 is just very much faster than K minus 1. If B or K2 or both or either very large relative to this term, this K minus 1 term goes away. The new rate law can be approximated as K2, K1 times concentration of A times concentration of B divided by K2 times concentration of B. The K2 and the concentration of B terms fall away, cancel out. We're left with K1 times A, which is the typical rate law for an Sn1 reaction, where the rate of appearance of product 2 only depends on rate constant K1 and on the concentration of A. But this equation also explains why early on you do need some concentration of nucleophile. If, on the other hand, if the concentration of nucleophile B is small, then the K minus 1 term in the denominator dominates. Concentration of B does not cancel out, and we are linear and first order in concentration of B. So that would be in this region of the plot where you could plot rate versus initial concentration of B and see basically a linear relationship. And finally, we mentioned the prediction based on this simplified version of the rate law that if we increase the concentration of product 1, we ought to decrease the rate of the reaction. This makes sense because if you have too much of product 1, it will intercept intermediate when it forms and go back to starting material. And you can actually test this, and this is adding exogenous or external amounts of product 1 before you do the rate experiment, and seeing what that does to the rate can be a good way to see whether a mechanism functions by this or whether a reaction functions by this mechanism. If these conditions were true, if B0 is small, or if K minus 1 were fast, or if product 1 concentration were large, we'd expect to see a linear dependence of rate on 1 over the product concentration. So that's called product inhibition, and we see it plenty of times also not only in organic reactions, catalytic reactions, but also in Michaelis-Menten types enzyme kinetics and reactions. All right, we're going to apply what we've learned here from the steady state approximation in another context, and this is going to be the context of a rapid prior equilibrium. So as always, it's probably best to think about this in terms of an example reaction, and by prior we mean before the rate determining step, before an irreversible step. So as an example, let's take the reaction of tert-butanol under acidic conditions. and in the presence of Cl minus to give the alkyl halide and water. Okay, so let's write out the elementary steps of this reaction mechanism. Presumably, the first step would be protonation of the OH group by H3O plus to give you this oxonium ion, where OH has been turned into a good leaving group, and then the conjugate base of hydronium, which is water. And we're going to assume that this equilibrium is fast, such that, fast relative to subsequent steps, such that we're going to say it's always in equilibrium. That is, as soon as we pull this product, this oxonium ion, away for a subsequent step, the equilibrium adjusts basically instantaneously. Okay, the next step of the reaction is for the oxonium ion to have the leaving group leave to give you carbocationic intermediate I and water. And we anticipate this to be reversible because you're going to a high energy intermediate. So the forward rate will be K1, the backwards rate will be K minus 1. And let's, for the sake of our discussion, we'll call the alcohol ROH, and we'll call the oxonium ion ROH2 plus. Then, and the reaction is reversible because water could react with intermediate I to go back to oxonium ion ROH2 plus. But alternatively, that high energy carbocation I could react with nucleophile Cl minus in an irreversible step to give the final product. Okay? All right, so let's figure out how to deal with this reaction. First, let's set it up as we have in the past. We'll say that the appearance of product is equal to some rate constant K2 times the concentration of intermediate I times the concentration of chloride. Okay, fair enough, but we don't know the concentration of I. So let's use the steady state approximation for I. All right. So to do that, we assume that the rate of change in I as a function of time is basically equal to 0. So we're going to write all of the terms that lead to formation of I. And those terms that lead to the formation of I will be positive terms. So K1 times the concentration of ROH2 plus equals, is where we get I from. Now, how can we lose I? Well, we can go backwards. K minus 1 times H2O concentration. Going backwards could get rid of I and give us ROH2 plus. And then similarly, we could lose I by having, and I'm sorry about that, in this K minus 1 term, we absolutely needed the concentration of the intermediate. And then in the K2 term, we also need the concentration of intermediate I times the concentration of chloride. As before, we can rearrange this, and I will factor out I. And if you need to pause to do the algebra yourself, that's fine. K minus 1 times the concentration of water plus K2 times the concentration of Cl minus equals K1 times ROH2 plus. Okay, and so we can then write an expression for the concentration of I. And that will equal K1 times concentration of ROH2 plus divided by K minus 1 times H2O plus K2 times Cl minus. So far, you're not seeing anything different from what we saw before, but the problem is we don't really know what this concentration of ROH plus is. All we know is that that concentration of ROH plus is immediately replenished by this equilibrium. So let's see if we can write down an expression for the concentration of ROH plus that is related to things that we know or can know. This equilibrium constant KEQ equals the concentration of ROH2 plus times the concentration of water divided by the concentration of alcohol divided by the concentration of hydronium. Okay? So if we wanted to, okay, so this is how we write the equilibrium constant for that reaction that replenishes ROH2 plus from hydronium in the alcohol. But we ought to remind ourselves that we know what the pKa of this oxonium ion is, that the pKa refers to the following acid dissociation reaction where Ka is going to equal H3O plus times the concentration of alcohol ROH divided by the concentration of oxonium ion. Or in other words, so we know this, that's a constant. So in other words, the concentration of oxonium ion equals the concentration of H3O plus, which we can know just by adjusting the pH, times the concentration of alcohol ROH, and we can know that's what we supply at the beginning, divided by Ka. And if we do that, then we can change that expression for I into K1 times ROH times H3O plus divided by Ka for ROH2 plus times K1 times the concentration of water plus K2 times the concentration of chloride. And I meant K minus 1 times the concentration of water. And then I come back to our expression for the formation of product here. K2 times the concentration of I, which will be K1, times ROH times the concentration of H3O plus, divided by Ka times the concentration of K1, times the quantity K1 times H2O concentration plus K2 times Cl minus concentration. And we'll have the Cl minus concentration here as well. We've here just substituted in, oops, all of this in place of this. And then all of this in place of this. Oops. So here's our more complicated rate law derived from the steady state approximation. But we can make some simplifying assumptions. If the K-1 reaction step, that is going back from carbocation to oxonium ion, is slow relative to K2, then the rate law would simplify. The K2 and chloride terms would cancel out. And my reaction rate would depend only on rate constant K1, acidity acid dissociation constant Ka, and the concentration of starting alcohol and the concentration of hydronium. That is only on the amount of alcohol and pH. All right, so let's use this approach to try to make some predictions about a couple of different alternative reaction mechanisms for the following reaction. So this will be the reaction of benzoyl chloride, which we'll call A, with alcohol B in the presence of a catalyst C, to give me ester product 1 and chloride leaving group 2 and pyridinium group P3. All right. So let's present some potential reaction mechanisms and then consider what the implication for the rate ought to be. Let's imagine that in the first step, A reacts with alcohol B in typical nucleophilic acyl substitution in a reversible step to give you the following cation, oxonium ion, and let's suppose that in typical nucleophilic acyl substitution fashion, alcohol B reacts with starting material A to give you the following positively charged intermediate, which then undergoes irreversible collapse of the tetrahedral intermediate to give you this cationic, this oxonium ion, and Cl minus is a leaving group. We'll call this intermediate and chloride, let's say, is product 1. This oxonium ion will be product 2. And then the ester and the pyridinium ions will be products 3 and 4, if that's okay. Then in a fast subsequent step, pyridine acts as a base to remove the proton to give you the following molecule P3 and then the pyridinium ion P4. All right, so we're saying that the K2 step is the rate determining step. By that, we mean that the appearance of product 3, which is what we're interested in, is the same as the appearance of product 2, because as soon as product 2 appears, it immediately goes on to form product 3. All right. And that will be equal to K2. The rate of appearance of product 2 will be equal to K2 times I. And then we can use the steady state approximation to say that the rate of change in concentration of I should be equal to 0, which means that K1 times A times B minus K minus 1 times I minus K2 times I are all equal to 0. And we could proceed on with the steady state approximation there. The concentration of I equals K1 times A times B divided by K minus 1 plus K2. And then dP2 and over dt should be equal to K2 times A times B. Sorry, we're just substituting in all of this for this. K2 times K1 times A times B divided by K minus 1 plus K2. All right. Well, what do we notice about that particular reaction mechanism? Pyridine is not in the rate law. So we can test that prediction, see whether the rate depends on pyridine concentration or not. If it does depend on pyridine concentration, then this mechanism can't possibly be the right mechanism. Suppose then we propose an alternative mechanism in which benzoyl chloride reacts with pyridine which we said is C, so A reacts with C, through some equilibrium process K1 and then the reverse rate K minus 1 to give you tetrahedral intermediate I, which then would undergo collapse to give you the following intermediate I2. And then let's suppose that the subsequent step, which would be K3, the reaction of I2, intermediate 2, with alcohol B to give you the following tetrahedral intermediate let's suppose that is fast, as is collapse of tetrahedral intermediate 3 to give you the protonated ester and regenerate pyridine C. And then reaction of that ester with pyridine to give you your final product. And the pyridinium ion. Okay, so this is complicated. But if we assume that everything after K2 is fast and irreversible, then the appearance of our final product, which I think above we called product 3, the rate of appearance of product 3 with time should be equal to the rate of appearance of intermediate 2 as a function of time, which should be equal to K2 times the concentration of intermediate 1. Well, what is that concentration of intermediate 1? We don't know, but we can use the steady state approximation. Rate of change in the concentration of intermediate 1 equals 0. So we'll write all the terms that contribute to intermediate 1, K1 times A times C, minus K minus 1 times intermediate 1 minus K2 times intermediate 1. And then we would see that the concentration of intermediate 1 equals K1 times A times C concentration divided by K minus 1 plus K2. And therefore, the rate law would be K2 times K1 times A times C divided by K minus 1 plus K2. And that's assuming that we're using the steady state approximation on intermediate 1. And so what we would see in based on that assumption is that pyridine C would be in the rate law. So you can easily discern between these two mechanistic schemes by testing the rate, formation of product. If pyridine is involved before the rate determining step, pyridine will be in the rate law. If it's involved after the rate determining step, as it is here in mechanistic option 1, it won't be in the rate law. Now, as you're going through this, you might ask, how do I know that K2 is irreversible? Why couldn't this be reversible and a subsequent step be irreversible? Yes. Could you deal with that situation? I think so, but you won't be required to right now. And there would often be some simplifying assumptions that you could make depending on what the slow step is. For example, if the slow step were step 3, then probably for the formation of intermediate 1, you could assume a rapid pre-equilibrium, and then probably for intermediate 2, you could use the steady state approximation. All right, now this is how you can begin to tell between a couple of different mechanistic options. All right, finally, in the last few minutes, I want to introduce a new way of thinking about reactions in which more than one bond is changing. You've seen reaction coordinate diagrams before, where we usually have energy on this axis, and then what we've said is reaction progress or reaction coordinate. We've been very generic about that, and we've said energy, you proceed from starting material through a high energy transition state to products as the reaction progresses. For some simple reactions where only one thing is changing, suppose a bond is breaking, reaction progress could be the length of the bond breaking. However, there are reactions where more than one bond breaks / forms, where more than one thing is changing. The classic example of needing to consider more than one reaction coordinate is in dealing with the question, is a reaction mechanism Sn2 versus Sn1? So in substitution reactions where you have a starting material let's have this be a leaving group and some nucleophile. As you go from starting material to products, you form a new bond between the nucleophile and the carbon, and the leaving group leaves. And so you have two different things changing here. You have the formation of the nucleophile carbon bond, and you also have breaking of the carbon leaving group bond. And whether the reaction progresses via one of these happening first, followed by the other, or both of them happening simultaneously, is a difference between Sn2 and Sn1. For example, you can imagine a mechanism where, this is the Sn1 mechanism, where the leaving group leaves first, and then in a second step, the nucleophile comes in. So there's two steps. You sort of get 100% leaving group leaves, followed by 100% nucleophile comes in. Alternatively, there's the Sn2 mechanism in which the leaving group leaves and the nucleophile comes in, and in the same concerted step, here's what the transition state looks like, and maybe the transition state is 50% nucleophile carbon comes in and maybe 50% nucleophile and leaving group leaves. For the Sn1 reaction, the transition state is here somewhere between starting material and products, and the transition state might be something like, I don't know, 70% leaving group leaves, and maybe 0% nucleophile attacks. And so you've got two different things changing at once. And we can think about this we can develop a new way of thinking about this where we plot a reaction coordinate energy diagram, and on this axis we still have energy, and on this axis, say, we have nucleophile carbon bond formation from 0 to 100%. And on this axis, let's say we have carbon leaving group breaking from 0 to 100%. Okay? And then here, on our energy diagram, is our substitution products. 100% carbon leaving group broken and 100% carbon nucleophile made, bonds made. Okay? So you can imagine a pathway that would be sort of, and let's suppose our starting materials are here and our products are here. You can imagine a pathway that would sort of occur along this diagonal between 0 here, starting material in this corner, and products here. And this would be the Sn2 mechanism, where at the same time as a nucleophile comes in, the leaving group is leaving. And the projection of that pathway down onto this plane would be this diagonal directly from starting material to products. And there'd be a transition state here. This is the Sn2 pathway. And presumably the Sn2 transition state would lie here. And in the Sn2 transition state, you could say, okay, well, the transition state is whatever percent nucleophile coming in versus whatever percent leaving group leaving. At the other extreme, you have an option where the nucleophile doesn't come in at all at first, but instead the leaving group leaves, and that gives you a carbocationic intermediate. And so this is 100% leaving group leaves. And this pathway would be along this particular axis. We're not moving at all for the nucleophile to come in because the leaving group leaves first. And the projection down onto this plane would just be motion along this line. The transition state would be right here. And maybe we would see... Maybe we would see that transition state was pretty far along the line towards leaving group leaving. And then in a second step, now moving along the horizontal to the left and right axis would be the pathway where the nucleophile comes in. Okay? And this would be sort of in front. So, and maybe we can use shading to communicate this. This is the Sn2 pathway. This is the horizontal plane. And then this would be the Sn2 pathway. So we're sort of drawing this three-dimensional potential energy landscape. We can either go down the Sn2 pathway, or which goes across this diagonal, or we can go through the Sn2 pathway, which goes on this leaving group leaving trajectory first, and then nucleophile comes in. And of course, I've drawn this potential energy surface as though we were dealing with the methyl leaving group, where it's lower in energy to go through the Sn2 transition state versus to go through the Sn1 transition state. And so we'd say the reaction's Sn2. Now, this is kind of we've done the best we can here, but your text has some interesting images that are useful to help us figure out how this reaction situation would change if we started to change what our starting material was from methyl to ethyl to propyl, primary, secondary versus tertiary alkyl halides, primary, secondary versus tertiary carbocations. So I'm going to walk you through some of these diagrams, and then we cover it in greater detail in Lecture 5. So in A, you see basically what I drew for you above. Here is the Sn2 reaction coordinate, where the nucleophile comes in as the leaving group leaves. Here, on the other hand, is, the Sn1 reaction coordinate, where we first have the leaving group leave, and then in a subsequent step, the nucleophile comes in. Those are the two pathways. Now, what happens, and this is the Sn2 transition state, whereas this would be the Sn1 transition state. What happens as we go from methyl to primary? Well, the stability of that carbocationic intermediate will have lowered. That's going to lower the energy of the transition state and make that reaction faster. But one interesting aspect of that, one effect of that on the potential energy surface, is it's actually going to curve this Sn2 reaction a little bit more towards leaving group leaving rather than nucleophile comes in. So this is where the transition state used to be. This is where the transition state is now. Notice it's moved a little bit more, less to where it's moved a little bit away from nucleophile coming in part because you can withstand a bigger buildup of partial positive charge on the carbon when it's primary versus methyl. And then, of course, this is the Sn1 pathway that we're seeing. And so we could continue on. One of the interesting effects that you observe as you go from ethyl to now isopropyl or a secondary carbocation is now we've stabilized the carbocationic intermediate. That makes the Sn1 pathway even more favorable and it raises the energy of the transition state of the Sn2 pathway because of steric hindrance, and that makes it more favorable for the leaving group to leave a little bit more. So as we lower the energy of this corner of our potential energy surface, the Sn2 transition states gets pulled in that direction. And then finally, for T-butyl, as you might expect, the transition state of the Sn1 reaction coordinate is low enough in energy that, and Sn2 high enough in energy that Sn1 is our preferred pathway. Notice that in all of these diagrams, the pathway where a nucleophile comes in and then the leaving group leaves is totally out of the question. It's too high in energy, and that's generally true for carbon. This would be a Texas carbon containing intermediate, and that's generally not too high in energy to be accessible. All right, so sometimes it's difficult to draw these three-dimensional potential energy surfaces, and so what instead we do is we take a bird's eye or floating scythe eye view of floating scythe eye view of the potential energy surface looking down from above, and then we can plot. This axis is the reaction coordinate where leaving group leaves. This axis is the reaction coordinate where nucleophile comes in. The Sn2 pathway is shown in orange, whereas the Sn1 pathway is shown in purple. And as we stabilize the carbocationic intermediate, the Sn1 pathway becomes a little bit more favorable, and the Sn2 pathway gets a little higher in energy, and the transition state moves a little bit more towards leaving group leaving and a little bit less towards nucleophile attacking. We'll talk more about that next time, but these are called Moore or O'Farrell-Jenks diagrams, and they can be pretty useful in considering the impact of structural changes on the transition state.